Water slide decals. Some people hate them and some people love them. They take a lot of time and effort in the build, and it's normally done after painting, so there have been a lot of work already invested in the model. So there is certainly some pressure involved not to mess things up. Hot water will make the decaling process go a little bit smoother. How do you keep the water warm while you are placing all those decals and tiny stencils on your model? One way is to keep it in a thermos bottle and replace the water as it cools down. Another way, which is a more reasonable method, is to get an electric cup warmer and use that to keep the water warm. There are USB-powered versions and more powerful ones that plugs into a power outlet. But this ludicrous project is not about being reasonable. What good is a hobby if we can't go crazy, right? Let's build a totally over-engineered heated decal bath. Okay. Let's get our feet back on the ground again. Heating 1 milliliter of water 1 degree Celsius requires 4.2 joule in energy. This equals 4.2 watts for 1 second. So if we assume a room temperature of 25 degrees, we get a total of 3150 joules. If we divide that by 180 seconds, we end up with 17.5 watts of power. I have been using a plastic tray for my decaling so far, but a metal one is preferable since it transfers heat better. The simplest way of building a heat bed is to use a large number of resistors and glue them to a metal plate. But I wanted to use the copper traces of a PCB as a resistor, similar to what is used in many 3D printers. With a 12-volt DC power source, an 8-ohm resistance will produce 17.5 watts. To figure out the dimensions of the copper trace, I went online to use a trace resistance calculator. Standard copper thickness is 1 ounce per square feet, and if we assume a trace width of 0.5 mm, we will need an 8 meter long copper trace to get 8 ohms. That seems like a lot. I wonder how big this heat bed will be. The PCB design were done using KiCad, and it's a free software that is very powerful and easy to use. I was able to squeeze in a bit over 8 meters copper trace on a 10 by 10 centimeter square, and that fits the metal tray from IKEA quite well. I'm using my trusty old breadboard for prototyping the electronics, and it also serves as a software development platform until I have a final electronics design ready. While I was waiting for the Heatbed PCB to get manufactured and shipped back to me, I made a mock-up of the heatbed and I attached the temperature sensor to it. For software development, I'm using Atom Editor with a Platform IO add-on. I prefer this environment over the Arduino IDE any day of the week. The major feature of the software is the temperature regulator, but a good user interface is also important, of course. I wanted to be able to monitor the heater power and also have a reading of the actual temperature. I decided to use a PID regulator. It's a well-established method of controlling temperature, used a lot by the process industry. So I started like most people do, looking at the theory and implementing my own version of it. I soon found out it's much harder than it looks. But I found this great blog on the internet, made by Beauregard, that basically is a walkthrough of all the rookie errors people like me do. In the end I used the PID regulator library provided in Platform.io, but it's written by Brett, so it's the same code as on the website anyway. I will not go into details about how a PID regulator works, at least not in this video. But its behavior is controlled by 3 parameters, P, I and D, which has to be tuned individually. But more on that later. Okay, but how does the software work? There are 2 buttons for setting the desired temperature. The range is limited between 30 and 50 degrees Celsius. There is also a small menu system where I can adjust the tuning parameters of the regulator. And I can also choose between Fahrenheit and Celsius. And finally I can store the settings in a non-volatile memory. To be able to tune the regulator, I attached a serial port to the Arduino and started to collect the measured temperature data into a text file. The text file was later imported into a spreadsheet program, so I could analyze the performance of the regulator and make my adjustments. With the software basically completed, I moved on to make printed circuit boards for the control electronics. Again, KiCad proved to be wonderful software to work with, and I was able to design a PCB with both surface and through-hole mounted components in less than a day. But the coolest thing is the 3D viewer, where you can look at the 3D rendering of the final product. KiCad also have an export function, so you can save that 3D model into a step file. This leads us into the final part of this video, design of the mechanical parts. The housing is designed around the heatbed PCB and the metal tray. The control PCB is placed at the bottom of the housing, and the tray lays directly onto the heatbed PCB. The temperature sensor is pressed against the outer wall of the tray. The front PCB and OLED display is screwed onto the front panel, and I designed a lens for the display and a small light guide for the blue and red status lights. Okay, we have departed quite a bit from scale modeling right now. But in the next episode we will start to assemble everything and bring it all together. So stay tuned for that. Thank you for watching.